Hey guys, Mr. B here. In this video, we're going to be going over the chapter 10.2 notes on moles and mass. So you're going to be learning how to convert between moles and grams, as well as moles and volume. So how to convert between moles and liters, right? So in this picture here, they show you a jar of jelly beans, and the question says is, how could you guess the number of jelly beans in this jar? And I'm sure you've ever gone to like a county fair or something where sometimes they have like that jar of candy, and they're like, guess how many pieces of candy you think are in here. And if you can get it right or within like a certain number, you get a gift card for whatever. Now you could try to sit there and like count them. Obviously, the whole point is that you don't have enough time and you can't see them all, so it'd be impossible. But the best way to do it would be you could try to determine how much are in there by mass. Like you could, try to think like, well, how much does one jelly bean weigh and how much does a whole jar weigh? And then maybe it feels like it's 100 times more, or 10 times more. Or maybe a jelly bean takes up, this much space and this whole jar is like this many liters. And so you could just like do a really quick math calculation and probably estimate it that way. Either way, we're going to learn how we can count and figure out the number of particles in different samples and substances using grams and liters and moles. Okay, so there are some equations here that they have to begin with. Again, we're going to be using dimensional analysis and converting, so I don't really think of these so much as equations, more of just they're showing you the conversion and how the conversion factor is set up to cancel units. Either way, if you're an equation kind of person, this can be helpful for you if you want to try like memorize these or something. We're just going to be using dimensional analysis. So, all right, here we go. Oh, sorry, apologize. So first it says, how do you convert the mass of a substance to the number of moles of that substance? So in the previous video, we learned about molar mass. And molar mass is the mass in grams of 1 mole of that material. Okay. Now remember, molar mass can be found by looking at the periodic table. So real quick, let's just jump to the periodic table here so we can remember. So remember that this number that is a decimal underneath any of the symbols of any element, that is the atomic mass, which is in atomic mass units, but it also is the molar mass. So this number, like for carbon, 12.011, this is basically saying if you had 12.011 grams of carbon atoms, that would be equal to 1 mole of carbon atoms. Okay? So the number here, again, this is the molar mass. So if we want to know how much does 1 mole of any element weigh in grams, all we'd have to do is look on the periodic table and it will tell us that way. Okay? So we can use that molar mass to convert between moles and grams because it is a fraction. Okay, so they kind of show it here. And if you flip the fraction around, you can then cancel out different units. Now you'll notice here that there's no specific number. It is mass in grams over 1 mole. This mass will change depending on the substance you have. So it's not a set number. Like Avogadro's number is a set number, right? 6.02 times 10 to the 23rd. Molar mass is not. Okay, molar mass depends on the material. So it's not a set number, but we can find it very easily. So let's take a look at a first practice problem here. We're going to delete this picture and insert a text box so we can do some typing. Now I am going to be doing most of the math work here on paper. So just because I can't really do the math work very well by typing it out, and it's easier for me to show it by doing it by hand on paper. So, all right, it says the aluminum satellite dishes in figure 10.8, which we just deleted, are resistant to corrosion because the aluminum reacts with oxygen in the air to form a coating of aluminum oxide. And they do give us the chemical formula for that. So Al2O3. We're going to need this to find molar mass. This tough resistant coating prevents any further corrosion. What is the mass of 9.45 moles of aluminum oxide? All right, so again, when we're doing conversion problems, it's very important to understand what it is they want us to get them at the end. Like, what's the answer they're looking for? What are the units at the end they want? And what's the number we need to start with? So we are starting with 9.45 moles of aluminum 2O3. So aluminum oxide, okay, so Al2O3. And they're asking what is the mass, which means our final answer is going to be some number of grams of this material, okay? So in order for us to do this, we are going to need to know the conversion factor between how many grams is 1 mole of Al2O3 so we can convert. All right, so we're going to need to go onto the periodic table to check this out. So let's go just take a look real quick one more time. So aluminum has a molar mass of 26.982. We're going to round to whole numbers just because it makes it a little bit easier. If you want to take it exactly as 26.982, you can if you really want to be precise, but it's fine to take whole numbers if the problem doesn't really clarify or specify they want it really specific. So we're just going to say 27 grams per mole for aluminum. Oxygen is 15.999. It's basically 16. So aluminum is 27 grams per mole. Oxygen is 16 grams per mole. So let's go back to our chart here, our notes. So for Al2, it's going to be 27 grams, and we're going to times that by 2 because we have, of course, 2 of them. I'm going to do this on my calculator here real quick just to make sure I don't mess up on the math doing it in my head. So this gives us 54 grams from the aluminum. And as for the oxygens, those are 16 grams apiece. So we're going to times that by 3 because there are 3 of them. So again, I'll do this on my calculator, make sure I don't mess up the math in my head. So this is what we have, okay? We're going to add these two together. So the molar mass for Al2O3 is going to be equal to 54 grams plus 48 grams. So I get 102 grams per mole. Okay, this is a fraction. So it's basically saying that if we had 102 grams of aluminum oxide, we'd have 1 mole. Or if we had 1 mole, we'd have 102 grams. Now we don't have 1 mole, we have 9.45 moles. So we have way more than 1 mole, which means we're going to have way more than 102 grams. Okay, we're going to have way more than 102. So I'm going to do the math now on paper here. So I'm going to switch my camera. Okay, so what we're going to do here is we're going to write out what we're starting with. So we are starting with 9.45 moles of Al2O3. And the conversion factor we know is for every 102 grams of Al2O3, that is 1 mole of Al2O3. So this is our conversion factor, okay? And of course, we are going to be ending in grams of aluminum oxide. So let's set up a conversion table. This fraction is going to go up here in our conversion. Since we're starting with moles of Al2O3, we want the 1 mole of Al2O3 on the bottom of our fraction so that it cancels. And we'll take the 102 grams of aluminum oxide and put it on the top like this. Okay, so again, this way we have moles on top, moles on bottom. Those will cancel out with each other. And so now we know that our math here is correct because the unit we have left is grams, and in our answer it's grams. So now we just have to do the math, which is, remember, we're going to multiply all these numbers on the top, divide by all the numbers on the bottom. So on our calculator, we're going to take 9.45, and we're going to multiply by 102, and then we can divide by 1, or you can skip that part because it's not going to change the number. Okay, so we got 963.9. We are going to round to 3 significant figures because the number we were starting with had 3 sig figs. So we would take the 9, the 6, and the 3, and then the 0.9 would round the 3 up to a 4. So our final answer here is going to be 964 grams as our final answer. Okay, so let's go back to our notes here. And this is going to be 964 grams of aluminum oxide, which again makes sense because we knew that if we had 1 mole, it would be 102 grams, and we have way more than 1. We have 9.45 moles, so this is way more than 102, so that makes sense. All right, let's take a look at another example here. So it says when iron is exposed to air, it corrodes to form red-brown rust. Rust is iron 3 oxide, and they are giving us the chemical formula. How many moles of iron 3 oxide are contained in 92.2 grams of pure Fe2O3? All right, so this problem is just like the previous one, only now, rather than starting with moles and going to grams, we're starting in grams and going to moles. Okay, so we're basically going to be doing the same exact thing. We're just going to be kind of doing it in reverse. So again, it's important to write down what information we are starting with and what we're trying to solve. We are starting with 92.2 grams of Fe2O3, and we are going to convert that into moles of Fe2O3. Okay. In order for us to do this, we are going to need to know the conversion factor between grams and moles, which is molar mass. So we need to know the mass of 2 irons, and we need to know the mass of 3 oxygens. Okay. So again, let's go look at our periodic table to make sure that we know these numbers. So iron here is 55.845. Again, I'm going to round that up to 56 just because it's close enough to 56. We'll just say 56. And oxygen is 15.999, which we'll say is 16. So iron is 56, oxygen is 16. So let's go back to our notes here. So iron was 56 grams. We're going to times that by 2 because there are 2 of them. So this gives us 100 and... hold on, let me make sure I do this right. 56 times 2. We get 112 grams for the iron. The oxygen is 16 grams. We times that by 3, which gives us 48 grams. So the molar mass of Fe2O3 is going to be 112 plus 48. We get 160 grams per mole. Okay, so there's our conversion factor. So now that we have all this information, again, let's switch over to paper so that we can do the math out. All right, so again, I want to write down what I know, which is we have 92.2 grams of Fe2O3. We are going to convert this into moles of Fe2O3. And we know that the conversion factor is 160 grams of Fe2O3 for every 1 mole of Fe2O3. Okay, now again, just thinking about this logically, if we had 160 grams of this material, we would have 1 mole. We do not have 160 grams. We only have 92.2. So we are not going to have 1 mole. We're going to have less than 1. So our answer is going to be less than 1, probably 0 point something. But we'll do the math out obviously anyway. So set up our conversion table. Since we're starting with grams of Fe2O3 here, we're going to have the 160 grams of iron 3 oxide on the bottom of our fraction and the 1 mole of Fe2O3 on the top of our fraction so that the grams cancel. Okay, so then math-wise, we can take 92.2 times 1, divide by 160. Again, if you want to skip the times 1 part, you can. So we're basically just going to take 92.2, divide by 160, and we get this, a lot of decimals here, 0.5765. Our starting number was 3 significant figures, so we're going to take this to 3 sig figs. So 0.576, the 2 will keep the 6 a 6. So 0.576 moles, which again makes sense because we already knew that it should be less than 1. Because if we had 160 grams, that would have been 1 mole, but we only have 92.2 grams. So our answer should be less than 1, which it is. So this looks good. So again, back on our notes here, our final answer is 0.576 moles of Fe2O3. All right, cool. Okay, so that is dealing with grams and moles, but of course, measuring the mass of something is only one way that we can find how much material is there. A lot of times we also will deal with volume, right? Let's say we're dealing with a liquid or a gas. It's a lot harder to find the mass of those things. Now, granted, you could find the mass of a liquid. You could put a container on a scale. You could zero the scale. You could pour the liquid in, and then you could see its mass. So that's one way to do it. Gas is, though, a little bit more challenging. So a lot of times we measure these things in volume. So there is a way, of course, to relate volume in moles. So Avogadro, the scientist who developed the idea of the mole, also had a hypothesis that stated that equal volumes of gases at the same temperature and pressure will contain the same number of particles. Okay, now, when it comes to gases, if you increase the temperature of a gas, okay, so you make it hotter, the gas will expand. Okay, that is because gas particles are constantly bouncing around like this. They have a lot of energy. If you increase the temperature, you are giving them more energy, which causes them to bounce around more, which essentially makes them push on the container that they are in and expand it and make their volume get larger. Okay. Likewise, if you cool their temperature down, then you remove some of the energy that they have, and then they start moving around less. They move more slowly, and the volume that they have then goes down, so they take up less space. Likewise, too, if you increase the pressure of this gas too, so if you pressurize it, like you were to smush it down like this, right, you would reduce the volume. Or if you were to have less pressure, like a big container, gases will spread out to take up the entire space of the container that they can be in. So a lot of times when we are trying to determine how many particles of a gas are in any given space, we do so at a very specific temperature and a very specific pressure. Okay, so we call this standard temperature and pressure, or STP for short. It is 0 degrees Celsius, which is basically the freezing point of water. So that would be 32 degrees Fahrenheit. And a pressure of 101.3 kilopascals, or 1 atmosphere. And that is basically the amount of pressure at sea level that the atmosphere pushes down on your body all the time. So if you don't realize that there's constant pressure pushing down on you, because there's literally like miles of gas above your head that are just like sitting on top of you. Sort of like, like we're like lobsters on the bottom of an ocean, but instead of being on the bottom of an ocean of liquid, we're on the bottom of an ocean of gas, right? There's all this gas above us that just squishes down on top of us, just like lobsters are at the bottom of the ocean, and there's all this liquid water that's pushing down on them. They're used to the pressure, so for them, they don't really realize it, and same with us. We're used to the pressure too. We don't realize or feel this pressure pushing on us all the time, but there is, okay? So standard temperature and pressure is 0 degrees Celsius and just 1 atmosphere, or basically just the pressure of a regular room, so you wouldn't be in a vacuum chamber or anything like that. And at standard temperature and pressure, 1 mole, or 6.02 times 10 to the 23rd particles of any gas will always occupy 22.4 liters of space. Okay, this is a constant number. This is what we call molar volume. So if you take any gas, you put it at STP, and you have 1 mole of that gas, it will take up exactly 22.4 liters of space. Doesn't matter what gas it is. So this is another conversion factor that we are going to use. Okay, we can write it as a fraction as shown here, with the 22.4 liters on the top and the 1 mole on the bottom, or we can flip it around and then we can do conversions with it, just like we can do conversions with Avogadro's number or molar mass. So, excuse me again. Let's take a look at another example here. So, sulfur dioxide, SO2, is a gas produced by burning coal. It is an air pollutant and one of the causes of acid rain. Determine the volume in liters of 0.60 moles of SO2 gas at STP. All right, so this problem, again, it's important for us to know what it is that we're starting with, what we're ending with. So they want us to determine the volume, which means that our final answer is going to be in liters of SO2. Okay, so volume is typically measured in liters. And we are starting with 0.60 moles of SO2 gas. Okay, so we're going to be calculating liters. Now, in this problem, because we're not dealing with mass, right? They're not asking us to do anything with mass. They're not giving us any numbers in grams. They're not asking us to find a mass. We do not need to know the molar mass of this material because there's nothing to do with mass in this problem. All we need to do for this problem is, because they're asking us to find volume and they're telling us that this gas is at standard temperature and pressure, or STP, we know that 1 mole of SO2 gas is going to be equal to 22.4 liters of SO2. Okay, so 1 mole of this gas will be 22.4 liters of this gas because it's at standard temperature and pressure. And we do not have 1 mole, we only have 0.6 moles. So we're not going to have 22.4 liters, we're going to have less than that, right? But we can calculate it. So let's switch to our paper again, and let's just do this math out. Again, we'll show the conversion. So we are starting with 0.60 moles of SO2. We are going to be ending in liters of SO2. The only conversion factor that we need is for every 22.4 liters of SO2, that is 1 mole of SO2. Okay, so here's our conversion factor. And this conversion factor has liters and moles, and we have moles and liters in our problem, so this is all we need. We just need to set it up right. So since we're starting with moles of SO2, we are going to have the 1 mole of SO2 in our conversion on the bottom, the 22.4 liters of SO2 on the top. This way, again, moles of SO2 will cancel out. And the unit then that we are left in is liters, which is exactly what our answer wants. So from here, we just need to do the math. So we're going to take 0.60 times 22.4, divide that by 1, and then we should be able to get an answer. And again, if you want to ignore the divide by 1 part, you can. So let's do our calculator here. So we're going to take 0.60 times 22.4, and then divide by 1 if you really want to. So you get 13.44. We are going to round this to 2 significant figures because this starting number has 2 significant figures. So we're just going to round this to 13. because the 0.4 would keep the 3 a 3. So the answer here we're looking for is 13 liters of SO2. And again, this should make sense because if we had 1 mole of SO2, oh, did not mean to do that. If we had 1 mole of SO2, okay, if we had 1 mole, we'd have 22.4 liters. We did not have 1 mole, we only had 0.60 moles, so we should have less than 22.4. We got 13, so that makes perfect sense. This is how we want to do that. So, all right. Now, there's one other part here that we're also going to look at, and this is using density to find molar mass. So this is really where our understanding of dimensional analysis is going to come into play, okay? So molar mass is sort of like density in the fact that it is very specific to materials, okay? It is an intensive property, which means that if you have, you can calculate the molar mass of any material and it will always be the same number no matter what, no matter how much fit you have, okay? So like water, for example, has the same molar mass all the time. It's about 18 grams per mole. It doesn't matter where you find the water. It doesn't matter, whether it's in China or the U.S. or in Canada. It's always the same. Just like its density is always 1 gram per liter, okay, or 1 gram per milliliter. Always doesn't matter. So molar mass is an intensive property. Density is an intensive property. We can use both of these and molar volume to calculate either one. Okay. So here's an example of what we're talking about. It says here, the density of a gaseous compound containing carbon and oxygen is found to be 1.964 grams per liter at STP. What is the molar mass of the compound? All right, so this problem might seem like it's difficult because they're not really giving us a whole lot of information. All they're giving us is we have some mystery gas that's made out of carbon and oxygen, and it has a density of 1.964 grams per liter. And again, it's some mystery compound. So it has a chemical formula of like CXOY, right? We don't know what the numbers are. And they want us to find the molar mass. So we need to get an answer that is in grams per mole, okay? Because that's what molar mass is. It's in grams per mole. So this problem, again, seems challenging because we go, well, what do we even do, right? Like, I don't, what am I supposed to start with? I don't know. They're only giving me one number. All right, so again, this is really where dimensional analysis is going to come in play. So let's change back to our paper here. And let me try to explain exactly what they're looking for us to do. So we are starting with 1.964 grams over 1 liter of this mystery compound, okay? Now this is the density. I'm writing it as a fraction though on purpose because I really want to show that it is 2 units. And our answer that they're looking for is going to be in the units of grams per 1 mole of this same material. So what they are looking for us to do, basically, if we look at this, all we need to do is convert liters into moles. Okay, because again, we are starting with grams per liter, and our answer is in grams per mole. So we don't care about changing the grams. We're not trying to convert grams. All we're trying to do is convert liters into moles. And they are telling us that this gas is at STP, which means that we can use the molar volume conversion to do this problem. Okay? So we are going to use 22.4 liters of this gas is equal to 1 mole of this gas. Okay, this is what we're going to be using. So if we take this conversion and we put it in our conversion table, again, now all we care about is the liters. We don't care about the grams. So if I look at this conversion, it has liters in it. And I want the liters to be opposites in my fraction. So I'm going to take 22.4 liters and I'm going to put it on the top of my fraction, because that way it's opposite from the 1 liter that I'm starting with down here. And the 1 mole is going to go on the bottom. Okay, now this looks a little bit weird because if you notice in all the previous problems that we did, we always had the unit on the top and then we put the unit on the bottom of the fraction. And then this time it's kind of opposite. We're starting with the unit that we're trying to get rid of on the bottom in the beginning, and then the conversion factor, it's on the top. Okay, as long as they're opposite, that's all that matters. So the liters will cancel. The units that we're going to have left once we do this is grams over moles, which is exactly what our answer wants. Grams over moles, right? That would be a molar mass. So we have the math set up right. And all we need to do is take 1.964, multiply by 22.4, and then divide by 1 and divide by 1. And of course, again, for those of you that are good at math or know that multiplying or dividing by 1 doesn't do anything, we're basically just going to take 1.964 and multiply by 22.4. Okay, so let's do it on our calculator here. So let's take 1.964 and we're going to multiply by 22.4. I'm just going to skip the dividing by 1's part. So we get 43.9936. Our starting number here had 4 significant figures. We should round this to 4. So 4, 3, and then the 2 9s would be our 4 sig figs. And this 3 will keep that 9 a 9. So our final answer we're looking for is 43.99. That is the molar mass of this mystery gas that they are looking for. Okay, so back to our sheet. You're going to have 43.99 grams per mole. That is the answer they're looking for. Okay, so I believe that is the last example problem here. Now, I didn't go over any of the practice problems. I have a video of me going over those, which are at the end here. So if you're looking for insight on how to do that, go watch that video. One of the final things they have at the end here is what we call the mole roadmap. So this is actually really helpful. I would recommend maybe writing this down somewhere or just knowing that this is there. So this kind of shows you how to convert between the different units with the conversion factors. So you'll notice that the mole's in the middle. The mole is a universal unit. Because the mole just means 6.02 times 10 to the 23rd things, you can have a mole of anything, which means you can convert any unit you can think of into moles. Okay? So if we have some amount of mass in grams, and we need to figure out how many moles that is, we're going to multiply by 1 mole over molar mass, or basically divide by molar mass. That's what this is saying. If we have moles and we need to go to particles, we can take the mole, the number that we have in moles, and multiply by 6.02 times 10 to the 23rd divided by 1. That will get us into particles. Or let's say we have particles and we are trying to convert into moles. We can take our number of particles and we can multiply by 1 mole over 6.02 times 10 to the 23rd, or basically take our number of particles and divide by 6.02 times 10 to the 23rd. Or likewise, if we have some volume in liters and we're trying to convert to moles, we can take our volume in liters and we can multiply by 1 mole over 22.4 liters, or basically take our number here in liters and just divide it by 22.4. So this little mole roadmap basically shows you how to convert between all the different things. And this is just, imagine there are multiply signs here. Okay, so like take this times 1 over molar mass. And this is known as multiplying by a reciprocal, which is where you take a fraction over 1 and you flip it, so it's 1 over. It's the same thing as just dividing. Okay, so this is really helpful, especially if you're really struggling with this conversion thing and knowing which conversion factors to use. This can be very helpful. So anyway, that is it for this section of notes. Hopefully that helps you. And again, if you want to see me go over the practice problems, you can go watch that one. So, all right, guys, I will see you in the next section, chapter 10.3. Bye.